lecture. We are lecturing right now Chapter 1. We're going to talk about fluid pressure and Pascal's law in particular. So that would be Pascal's law. And what Pascal's law entails is we're going to go ahead and draw a fluid tank. Let's see. All right, the fluid tank is going to have a large opening at one end. I'll describe this in more detail right now. And a kind of narrower opening on the other end. All right, so we have on each end we have a piston that's floating. We'll just put a little a shaft there and another piston here that should be around the same height and another shaft there. Okay, so in here, let me see if I can generate some fluid color. So let's color this fluid like a red or something, maybe a light red here. See if we can do that. Oh, didn't work. Maybe I have a leak in this model here. All right, so we're going to skip coloring that thing, but there's inside of here is a fluid, and what we have is we're going to have a force acting down on this piston here. Call that force F1, and then by pushing down here, it basically transmits through this fluid and pushes this piston up. A force 2. Because our pistons are roughly on the same horizontal plane here, then we use Pascal's law, which will tell us that the pressure at 1 is equal to the pressure at 2. And so what this tells us is the pressure. Now in here this is area 1 at the bottom of that piston. This is area 2. And so what we're saying here is that the pressure at 1 is equal to pressure 2 is the same as saying that the force at 1 divided by the area at 1 is equal to the force at 2 divided by the area at 2. And then, so from this we can get an actual leverage equation that tells us that we can go ahead and put force on the left and an area on the right. It tells us that the force at 2 over the force at 1 is equal to the area at 2 over the area at 1, which says that we are getting an increase in force. So if for example my piston here is has 5 times the area as the piston at 1, then it would be 5 over 1, right? So that means that my force at 2 would be 5 times as great as the force at 1. And this is how we create a leverage, or where we use this basically as a jack to lift cars or to lift heavy things. And so thus we have that equation. Okay. I'm going to go ahead and start a new demonstration here. All right. So now we're going to go ahead and talk about a manometer. So let's go ahead and write that down. Try to create a nice bright color here. So we're going to talk about a manometer. Now, what is a manometer? It's a pressure measuring device. All right, so to discuss a manometer, first we're going to talk about a fluid tank. And our fluid tank, let's go ahead and create the tank. Oh boy. All right, so great. Okay, so we're going to create a tank. All right, so that's our tank, and we're going to have three different types of fluid. The first fluid we're going to have up here, this pink colored fluid, and that's our first fluid layer. Let's just say that the fluid layer, I'll explain in detail right now what's going on here, but we say it takes up about this much space in the tank. Sorry that I went outside I went outside the boundary there. It's just a little difficult to. Okay, we'll just leave it. We'll leave it. And then the next color, we'll pick maybe yellow. Oh, it's so hard to draw with this thing. This is ridiculous. Well, let's say the fluid takes up an area like that. And I'm going to go ahead and fill it in. And I'm going to fill in the other one too. Though I think I may not get the right color here, but I'm going to fill this one. It was a pink one, huh? So just like a magenta color or something. And then we're going to go ahead and create the next fluid level. Let's make it a red. All right, so then we'll go ahead and write the, maybe we can just fill that in, see if, like that. Okay, so you have your fluid 1, your fluid 2, and your fluid 3. And so if we want to measure the pressure here at point 1, we need to get the contribution of each fluid. So as you go down, imagine this is a swimming tank, and you're going to get the total weight of this fluid section plus that weight of that fluid section plus that weight of the fluid section to give you the total force at the bottom there. And so the way we do that is we're going to need to know the heights here. So that's H1, H2, and H3. All right, so that's the height there. All right, so we need to know those heights. Obviously, we need to know the area. We don't need to know the area actually because it's one uniform area. If you could just imagine this tank has a uniform area throughout, then the area you don't need to know. It just kind of cancels out. So what we do is we know that there's a atmospheric pressure out here that's pushing down. So we know that pressure is equal to force over an area. So there's an actual resultant force from the atmosphere pushing down. So if we want the total weight or force at the bottom, what we do is and if we assume the area is uniform, then we can start by first starting here at pressure at the top. We say pressure atmosphere. That gives us the pressure there. Now we want to go to the pressure here and we start adding up the contributions there. So if we want to know the pressure there, it's the pressure or it's the total load at the top plus the weight of this pink fluid. So we're going to say it's plus density of the first fluid times gravity times the height of the first fluid. And then we want to know, I'm just going to change the color a little bit here. We want to know after we have the load here plus the load there. Now the load here is basically adding the load associated with the yellow fluid. So then we go ahead and we just say it's plus the contribution of that yellow fluid, which is rho 2 gravity times H2. And then lastly, at 1, we arrive to the bottom, and it's the contribution of that red fluid. So it would be the density of the fluid at 3 times the height at 3 plus, sorry about that. Let's do this right. Let's do this right. We don't have any confusion here. It's G times H3. And then we arrive to the bottom, and that's where we say is equal to the pressure at the bottom, which is 1. And that's how we arrive at the fluid. That's how, so we go ahead and just calculate everything on the left-hand side to arrive at the pressure at the bottom. Okay, so now we can discuss the manometer. So forgive me, this takes a little while sometimes for me to do this. Okay, let's discuss the fluid at the bottom there. Let me go ahead and color this. Now let's go ahead and set up an actual manometer that's used. We're going to go ahead. I'm going to draw a pipe, attempt to draw a pipe here. that of a certain cross section. Let's see, it's like that. And this pipe here, we're going to have, there's an obstruction in here, and just say it's paper scaling or something. There's a flow of fluid that's normally going in this direction here, and it's going in that direction, but so we'll just say it's fluid, and it's seeing an obstruction, so therefore we can assume that the pressure here is higher than the pressure there. The obstruction has the effect of lowering the fluid pressure as you go through it. So then what we can do is want to measure the pressure drop across this obstruction. So what we do is we put a manometer in there. So let's go ahead and the manometer is essentially a glass tube. I'm going to draw. Let's assume that's at a perfect angle there. This has a cross section, and a uniform cross section. And then there is a kind of a U bend down here into this glass pipe, and then it goes all the way up and taps that other end there. Let's go ahead and do that. We can try to do as best we can a uniform cross section. So again, that's what we have here is there's an opening here. I apologize about that. Let's see. Let's assume this is open to the inside of this pipe there. All right, and so now in order to, let's say we fill, before we go into that any further, let's say we have a fluid in here. And there's a secondary fluid here. So this is fluid 1 that we have going through this. We're just call it fluid, the blue arrows. Now there's a secondary fluid here, and because of the pressure differences, it experiences from a slight rise in height here, and I'll go ahead and explain what that is. Let's see if I can do this. I'm hoping I can fill this. Yeah, so there we go. So that's that secondary fluid, and we're going to say that the height difference, we're going to say that there is a height A from the pipe to this level here. We're going to call that A. And then we're going to say that from this level here to here, so that's the horizontal you go across here. And so therefore, this is H, basically, from level of this side of the fluid pipe to here. We're going to call that H. And then we're going to call this level here on the left of this second fluid A, and then we're going to call this actually, we're going to call over here B. Basically, horizontally from A to B, we just cross through here horizontally. Okay, so what's happening is there's the fluid's coming in here, a little bit's coming into the pipe, and it's pushing against this red fluid, and it's causing the height to go up here at a distance H. And then there is a distance A from that level to the entrance to the other side of this obstruction to this pipe. And if we didn't have that obstruction here, if we assume that there was constant pressure throughout here, then this fluid level would lower, and it would basically be the same as A and B would basically match up. Okay, so all right, so let's go ahead and use this manometer to find the pressure difference between 1 and 2. So to do that, we're going to assume first we start here. Now, the way I like to do is I'm going to create a little, borrowing from, do a little, actually, I'm going to do a red demon. All right, so borrowing from Maxwell, who envisioned, and I envision a little demon, so a little blue person, a little red person here, standing here like that. All right, so imagine there's this little blue person that's hanging out there. What's the pressure that this little, red person is experiencing? The pressure the red person experiencing, we're going to say that's P1. All right. Now we want to go next to our next interface, and that would be here. So what is the if the little blue red person takes a little dive into this tube and starts kind of swimming his way down here, so that's his little head, and he starts descending into this pipe here, and he ends up here on the surface, this interface, point A. What's the difference in pressure that that little red person's going to see? Well, that's so the person's actually getting, so is he experiencing an increase or decrease in pressure as he goes down this fluid? It's an increase, right? It's kind of like diving into a pool that as you go towards the bottom, it increases in pressure. So we're going to have to add to P1. So it's going to be, the pressure here is going to be the pressure at P1 plus whatever the pressure gain is from descending into the pipe, which is density of, we're going to call this fluid 1, the blue one here, fluid 1 there. I know it's kind of, probably should have colored it a different color, times gravity, and then we need to know the height difference between here and here. And so we don't care about the diagonal difference, we only care about the horizontal height difference. So that turns out to be A plus H. If you can see, A plus H gives us the distance from here to that interface. So it's quantity A plus H. Now, now that the little person's here, we do have a rule that says that we can go horizontally across. So like this little red demon was able to pop out of the fluid and just kind of walk like a tightrope and walk across here and end up, I'm going to change the color. Well, no, you can still see him. End up here. So a little red person ends up there. Now, he would have experienced zero pressure change because he stayed basically within the confines of the horizontal distance of the fluid. So the pressure at A and the pressure at B are the same. All right, so now he's here, and now he wants to float up to the top here. He wants to end up at this second interface there, which is basically where A little lowercase a starts. So what's this little person is going to experience an increase or decrease in pressure as he floats up this column of liquid? It would be a decrease, right? Because he's actually swimming back up the column, and so therefore it's going to be a subtraction there. And how much of a pressure decrease is he going to see? Well, we're still in the, actually now we're in a different fluid regime. So this stuff here is, we're going to call it, well, that fluid here, we're going to call it fluid 2. Oh boy. We're going to call it fluid 2. Let's say fluid 2. And that is basically, it's the density at 2 times gravity times what? So it is, well, how much did he travel up? H, right? So it's basically times H. So it's, let me write H here. So he decreased in pressure to here. And then now, to get through this last column of fluid, he goes back to fluid, swimming through fluid 1, which is the blue arrow indicated. So he also has to experience a pressure decrease because he's still floating up if he wants to get to this last portion there. And so therefore, we're going to do a subtraction. And now we're back to fluid 1 times, now the distance he traveled is A. And now he arrives to 2, and we're going to say now he arrives to 2, so we say that's equal to P2. And so now if we want to find the difference between the pressure at 1 and pressure 2, we could just basically cosmetically change this equation to give us P1 is minus, sorry, P2 is equal to, so the portions that have A cancel out because here is a rho 1g A, and then here is a minus rho 1g A, and so that actually cancels out, and we're left with rho 2 minus rho 1 quantity gravity times height. And so this turns out to be our equation to find the pressure difference across this obstruction. And so that's how we use a manometer. Okay, and so all you need for this manometer is to know basically the density of the fluid of what you're measuring, the pressure, And then the density of the fluid that's inside your manometer, typically it's something that's higher density, kind of like a mercury or an alcohol than what's in that you're measuring, so that the height, you minimize the height obstruction here, or a height uh, increase, times G times H, which is basically height that it travels up. Okay, and that is the end of this manometer lecture for now.